Okay, I think it's 4 minutes past. Might as well start. It's a bit early for a Monday, but we have to do it. All right. Yeah, first of all, I just want to say that the solutions to the quiz, will go up on e-learning, so you don't need to worry if you didn't make it to the tutorial. But I'd like to encourage you to go to the tutorials just to touch base with the tutor. You can ask questions about the course as well as emailing me anytime. And there'll be another one, number 2, going up probably this week. So you can have a look at that on Canvas. The idea of the quizzes is just to get you doing problems, looking at the material as we go along, rather than leaving it all to the last, which sometimes is unavoidable. I know with all the assignments and things that you have, but it's good if you can keep doing these the quizzes and looking at the notes as you go. What else do I think? I think nothing else to say. Remember last Friday we ended up with this slide here. This was looking at the structure factor for cesium chloride, and we ended up with this expression here, so that we had the form factor for the cesium atom, form factor for the chlorine atom, and these were your Miller indices. What we're going to do now is replace that chlorine atom with another cesium atom, and when we do that, you can see that we'll have a body-centered cubic cell. Okay? There'll be another cesium atom in the center, and what we're going to do is see how the structure factor is then. Okay? So this is what we would get. The only thing we're doing now is making these two both cesium, pull that out the front, and then you have this expression here. And when you look at this expression, you can see that you will get a 0 here when these H plus K plus L are odd. Okay, so this is kind of important because it means that for certain HKL, for the body-centered system, you won't see a diffraction spot when some of these Miller indices are odd. Okay? And this is kind of like a selection rule, a fingerprint of the body-centered cubic structure, if you like, and we'll see that a bit later on as we go through. Now, next we're going to consider the face-centered cubic structure and see if we also get some restrictions on the diffraction spot intensities for certain HKL. Okay, so what we're going to do is, the results are basically shown here, but let's just work through them slowly together so that you actually see how to do it as we go along. Okay, so, what have we got here? You always draw your cell. We've got a face-centered cubic structure. So in this case, it's, say, copper, FCC. So with our face-centered cubic structure, oh, thank you. Yeah, just call out if something's not right. So, okay, we've got atoms here at the corners, and then we've got atoms at the face-centered cubic sites. Say one up here at a half, 0. And then, of course, one at the origin. And, okay, let's just write them down. So 0, 0, 0. Another copper atom at a half, 0. That's this one here. Then we'll have another one at a half, 0, a half. And where is that one? Okay, if this is sort of A1, like the X direction, and put this as the Z direction, that is your y hat direction. Then there will be another one at 0, a half, a half. So those are the positions of our copper atoms in this conventional cell. So that's the first step. We need to know the positions of our atoms in the cell. And then we have to say, okay, what is our structure factor? Structure factor HKL is given as the sum over atoms J in your cell, the form factor of each atom species F of J. We've just got copper here, so that's okay. Then we have e to the 2 pi I H X of atom J plus K. These are your Miller indices. Y of atom J and L of atom J. So that's the structure factor. So all we're going to do now is substitute in the positions of our atoms and see what we get. So we have just copper, form factor of copper, let's see, e to the 0, because that's your atom at the origin. Okay. Then we get e to the 2 pi I H over 2 plus K over 2 for the next atom, plus e to the 2 pi I H over 2 plus L over 2, next atom, plus e to the 2 pi I K over 2 plus L over 2. Okay, so this is the way this is what we do. And let us work that out. So that's just 1 plus, sorry, I better turn this off. Sorry, okay. So we've got cos of pi H plus K plus cos of pi H plus L plus cos of pi K plus L. All the signs obviously go out. And we are left with the form factor of copper, 1 plus, you know, the cos function, when you've got an integer multiplied by pi, it just alternates between 1 and minus 1, depending on what that integer is. So we can write it as minus 1 to the H plus K. The other one will be minus 1 H plus L, and the other one minus 1 K plus L. So when we actually look at that and we think about it, we can see if we want to get a non-zero intensity, then this thing has to not go to 0, which means, say, for non-zero structure factor, and non-zero intensity, we need to have all HKL must be, does anybody know? They must all be even, okay, or odd, okay. So if they're even, this will go to 1, 1, and 1. We'll get 1 plus 1 plus 1 plus 1. We'll get 4. Odd number, yeah.
So can I ask, where do the signs go? Apart, or?
Oh, the signs, yeah, they go to 0. Because we've got a pi multiplied by an integer.
Oh, okay.
Yeah. So when these are all even or all odd, because when you add two odd numbers, you get an even number. So these will just go to 1 as well. Then we get the form factor. 1 plus 1 plus 1 plus 1 equals 4 times the form factor of copper. So what we can do is just have a little look. Say, you know, what if, you know, H is odd, K is even, L is even. What if we have a situation like that? Then we can just work that out. You will get 1 plus minus 1 to the, say, h plus k, that will give you an odd number, because odd plus even will get you odd, plus minus 1 to the h plus l, odd plus even, also get you odd, minus 1 to the k plus l, k plus l, even and even is an even. So you can see that you're going to get some cancellation going on. And, you know, you can make, to convince yourself you can try some other combinations, but unless they're all even or all odd, you'll always get a 0. So this makes a really good selection rule for FCC fingerprint. So if you've got your diffraction beams looking at you on the screen, and you notice that some spots are missing, and the spots that are missing that correspond to the situation where these are odd and even mixture, you know you've got an FCC. We'll see that. We'll do a little example of that and see how that works. I think that's fairly straightforward, just substituting in. But you can see, you know, you have to actually go through it to, you know, to see the results. But it's straightforward. Okay, so I'll leave that and come back. To here. So what have we got so far? Remember we did the simple cubic and we found no restriction on the H, K and L. We did the BCC when we substituted the chlorine for the chromium. We found that to get a non-zero intensity, we had to have H plus K plus L be even. We just did that when we came in. And now we have, for the face-centered cubic, we have learned that H, K, L must be all odd or all even in order to get a non-zero intensity. And these are called selection rules. Okay. So what we're going to work through now, well, actually, we're not going to work through it now because I want you to do this yourself. But it's the same procedure that we just did together in class. It's just the different structure. It's a little bit more complicated. What we have now is this zinc sulfide structure. Okay, we've got one atom of one species here and another atom of a different species here. If these were the same, you just have the diamond structure, right? This is just the diamond structure. So what we can do is consider this, to work this out, the structure factor, we can consider it as a cubic lattice, just like we did before for the FCC, with a basis of 8 atoms inside it. So this will be 1 atom of the basis, 2 atoms, 3 atoms, 4 atoms, 5 atoms, 6 atoms, I don't know, 7 atoms, 8 atoms, okay? They're written down here in any case. So we've got the positions of the zinc atoms. You can see now there's 1, 2, 3, 4. So it's a bit more complicated than the one we worked through together. And then you've got the bases, which are in these positions here. So you do the same thing. You do the sum over the species. First of all, you have species zinc here. And then you've done the same thing. You substitute in all the positions of your atoms into the structure factor, and so on and so on. All these zinc positions. This is the first one, just equals 1. Okay. The second one, a half, 0, a half, 0. The next one you would do would be this one, and then this one. Okay. Then you switch over to your sulfur, where you've got the first one, quarter, 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 quarter. Next one, 3/4, 3/4, quarter, 3/4, 3/4, quarter, and then you add 2 more to it. Then you do some working, just algebra, and what you find is you can pull out this factor in front of this. Okay, so it's a little bit messy, but you find you can pull this out, separate it into two kind of expressions. What you find, this is important, put a red box around it, is that you get a structure factor of the lattice. This is the structure factor of the lattice, which is just your cubic lattice. And then you get a structure factor multiplied by the structure factor of the actual basis, which is like all of the atoms inside it. So I've put that, yeah, just check that you get that for homework, or if you're convinced already, you don't need to do it, obviously. But by finding out this important fact, it allows us to be able to solve for some structures. Just another aspect about the actual intensity. Remember, it was proportional to the structure factor squared. We're going to put in a bit more in that proportionality constant. You also get this m here, which is the multiplicity of the particular HKL. Okay? So, for example, if we have, this was actually, I think it was on one of your quizzes, or it might be on your assignment, to find out how many of the 111 indices belong to that 111 family. There's 8 of them, and so this is called the multiplicity of the one. For example, if we have 111 here, m would be 8. 1, 2, 3, 4, 5, 6, 7, 8. If we're looking at a 100, we would have 6 being the m here. But as you can see, it's still only proportional to, so there's some other factors that get into that expression for the intensity. So what we're going to do is do an example and see how that. Imagine you're an experimentalist and you're sitting at your neutron scattering facility somewhere, and you've got some kind of material, praseodymium oxide, and you're not sure what the lattice constant is, and you don't know what its structure is, but you've been able to make measurements, and these are the results that you've got. So you've got the intensity of your peaks, and you've got some peaks here, okay, plotted as a function of 2 times theta. So you've got little peak A, B, big one C. So not only the angular position of these features is important, but also the intensity, and we'll see that shortly. First of all, we're going to focus on just the angular position and what that can tell us about, for example, we're going to determine the lattice constant of this material. And then we will figure out if it's FCC, BCC, or simple cubic. Okay, so this is what we do. I'll spend a little bit of time here on this table, and we might go through an example line just to see, make sure you understand. Okay, remember we had this relationship here between the interplanar spacing of your particular plane, HKL, the distance between 2 planes. Remember, it's equal to the wavelength used in your experiment over 2 sine theta. So this is the theta that we can read off from the experiment. And remember, that was equal to A, the lattice constant, divided by the square root of your Miller indices squared. So what you do, first of all, is these are your peaks, A, B, C, down to F, just here. First thing you can do is just read off 2 theta, just straight off from your experimental data here. So for A, it's at like 22.7. and so on. And then, using the expression here, we know 2 theta, so we know the wavelengths of the incident radiation. We can get an expression for the interplanar spacings just by evaluating this expression here. And because this is probably the first feature, the lowest angle, what you do here is just divide all of these other distances with respect to the first one. So 0.313 divided by itself is just unity. And the same thing to 0.27, sorry, this one divided by that one, this one divided by that one, and you get some numbers here, okay? What we're trying to do is determine from these numbers the HKL, okay? So when you look at these, you can see that they're somehow related to being a multiple or divided by 3 somehow. So if you recognize that you multiply this by 3, what you get is very near integer numbers. Okay, so if you multiply this column by 3, as written up here, we get 3, 4, 8, 11, 12, 16. These little deviations will be your experimental error. And so these are now just rounded up to the nearest integer. And that is equal to h squared plus k squared plus l squared, just from up here. Now this is the point where it may have lost you a little bit, unless you've had time to, go over it at home already. Let's just take a little back step and start off with, okay, we start off with what we know from before, lattice constant, h squared plus k squared plus l squared. And so squaring both sides, and we can just turn it upside down, multiply both sides by a, which we don't know yet, and we're just calling that n. Okay, so that's all we've done in that column over here. And we're just calling it 3dA on d squared. We don't know a yet. This is, at the moment, we don't know what that is. But from the values that we find, so for peak A, we know that this d could be rounded to 3, okay, when you just make it with respect to the first peak. So the only combination of h, k, and l that can possibly give you 3 would be if h, k, l are all equal to 1. There's no other way you can get it. So for peak A, we have the result HKL is equal to 1. So if we know the HKL, then we know and measure D, we can get a value for A. Okay. So we have here A is equal to D, just from 1. The HKL multiplied by h squared plus k squared plus l squared. And we had that for the first peak A that we are considering, D was 0.313 nanometers, and so that becomes, substituting 1, 1, 1, we get √3. And so that is 5.42 angstroms, using just peak A. Okay? And then what you can do is do exactly the same for the other peaks. For example, from peak B, we had that n, from peak B, we know D, we found that the closest integer was 4. And when you think about what HKL can give you 4, HKL, it can really only be a 2, 0, 0, or a 0, 0, 2, or something like that. And so, in this case, we can do the same thing. We can estimate A using the result of peak B, D, HKL, which in this case is 2, 0, 0. We had 0.27, 0 nanometers, multiplied by the square root of h squared plus k squared plus l squared, which was just the square root of 4. And then you get 5.04 angstrom. Okay, so it's very similar to your result from the first peak. Okay, and the difference between them will give you some estimate of your experimental error. So you can do that for all of the peaks, which has been done in the table. Not here, but on the next slide. Steve, yeah. Yes. I mean, at the moment, all we know is that these peaks correspond to scattering from some planes, okay? So we are just saying that, okay, A must be the smallest, the largest interplanar spacing, okay? So the lowest angle that we are getting. So we are just, we don't know A yet. So we are expressing the interplanar spacings with respect to the first one. And n is actually equal to a squared on d squared, which equals h squared plus k squared plus l squared. So basically, this feature here gives us the smallest ratio of these interplanar spacings, okay? So it will give us the smallest possible HKL. And this can be, how can I explain it? We don't know the actual lattice spacing, okay, but we know the expression for it here. So it turns out that this actually does correspond. Yeah, I'm not really explaining that well. Yes. Perhaps let me just think about that a little bit more, and I will, yes, see if I can. I mean, we have this relationship here. We have these measured peaks here. Yeah, yeah. And then, so what we are doing is we are saying the smallest angle feature here. We can easily get the interplanar spacing of that, and the subsequent spacings are smaller because they are at a higher Miller indice. So I'm getting there. I'm getting there. So let's see. So once we have determined we're trying to determine the HKL. That's what we're trying to do. Trying to determine the HKL. And we know the HKL are related in this way to the interplanar spacing NA. So if we make the ratio, I think basically it kind of falls out, but let me check that, because you can imagine what we are doing is we're making a ratio of the D's with respect to the smallest Miller indice, which will give the largest interplanar spacing. And when you put a ratio of these two spacings with respect to each other and substitute that in there, I think that's the key. But let me do that. Yeah. Okay. I think it's something. It's not too troubling. Okay. So once we find those Miller indices, so we've got to label those peaks with the Miller indices, and then we know this relationship between A and D. So if we've managed to find the HKL, then we can simply substitute them in. We know the D, which we just measure off. Okay? And so you get an estimate of the lattice constant from all of those intensities, and they're all pretty close together. And the deviation, as I said, gives you an estimate of the experimental error. Okay, so that's fine. We've been able to find the lattice constant. But what about the structure? So let's just sort of look having labeled the HKL, they are summarized up here. Okay. And then if we just make a table with all possible Miller indices, starting from the lowest index plane, or the lowest index, down to the higher ones, and working out the n that corresponds to them, writing down the multiplicity. We don't need that for what we're doing. But then we look at the Miller indices that we've got, and okay, we can see that we have the 111, we've got the 200, 220, and the 311, and the 222 and the 400. And we know from our selection rules that cubic can have any Miller indice and you'll get a spot. So you'll get an intensity for any HKL for cubic. For BCC, we would only get an intensity. Does anybody remember what to? I've forgotten briefly. Let me check. For BCC, we only get an intensity when. Come on, somebody must remember. When what? All even or all odd? Or all even, yeah? Good. So HKL must be all even. So we get a tick for, yeah, the sum, exactly. Yeah, the sum must be even. So that is even, even, okay? And you can see that that is not sort of what we've got. We have got 1, 1, 1 and 2, 0, 0, 2, 2, 0. And this is exactly where we should get the intensities for the FCC. Okay? So only these ticks, only these intensities do we actually get measured spots on. So that tells us we have the FCC structure from these selection rules. Okay, now we can do even more with this data. What we want to do now is we can also learn something about the scattering factor of the oxygen and praseodymium atoms in our material. So let's consider our whole thing again. Remember, we had the structure factor being written as a product of the structure factor for the FCC lattice and then a structure factor for the basis. Okay? We've kind of looked at the first part. Now we're going to concentrate on the structure factor for the basis here, involving the scattering strength for the praseodymium atom and the scattering strength for the oxygen atom. And this is obtained here, these expressions, by substituting in the positions for where these atoms are. Okay, so the praseodymium atom is located at the origin, and then we have for the oxygen atoms we have located at these positions here. That's how we get these exponential terms here. Okay, so this is the important table that one can get. So if we just concentrate on what we have here, these are the peaks that we have from our data. These are the HKL that we have determined from our measured data. Remember that the intensities were different heights, so those intensities are written down here. Now, what we can get from the theory that we have just gone through are expressions that relate the scattering strength, the B, of the oxygen to that of the praseodymium. Okay, so let's just go through that, the first one together. Let's just see how we actually get this 8 BPR squared. So, remember, let's say for peak A, and remember our expression for the intensity, it was, HKL equals C, M HKL, structure factor HKL, all squared. So we can, as done in that column here, we're just going to divide it through by C, which is a kind of unknown constant. And that's going to be equal or proportional to M HKL, S HKL, all squared. Okay? And this is the multiplicity, remember? And so if we focus on peak A, which was the 1, 1, 1, scattering from the 1, 1, 1 plane, M, 1, 1, 1. Remember, that was 8. So that already gets us the 8. So now we just need to work out the structure factor here, in this bracket here. So that was at the origin, the praseodymium atom. So well, let's just write it out a bit more. PR, remember we had B0, Then we had e to the I pi on 2, h plus k plus l. And then we had plus e to the I pi on 2, h plus k plus 3l. That's the position of the atoms. Okay. So when we substitute in the HKL, 1, 1, 1, that's the way we get what we are looking for, if you like. So we get e to the I pi on 2 times 3, HKL is 3, plus e to the I pi on 2, 1, 2, 3, 4, 5, there. So we end up with, let us think about this. We know that cos n pi on 2, that will always go to 0. And then the sine terms from these two will cancel. Yeah, they will cancel because you'll get 2 pi, 3 pi on 2 here, and then you'll get 5 pi on 2 there. So you only end up with that first term. And so this is where we get that term here. So for the next one, for B, you do the same thing, except you substitute in 2, 0, 0 for the h plus k plus l up there. And when you do that, you get this expression here. Okay, and the same thing for the other one. So you're getting a series of equations from which eventually you'll be able to find the ratio of the scattering length of the praseodymium atom to that of the oxygen atom. Let me go back here. Yeah, so you end up getting your completed table, and you can see some relationships. For example, if you look at the intensity of peak D, 24 scattering length of the praseodymium atom squared is equal to 3 times that of A. And you can see other relationships here between the intensities of the peaks. In particular, what we are, as I said, what we're wanting to do is get information on the scattering strength of the praseodymium and oxygen atoms to see how effective they are in scattering. If we make the ratio of the expression for the intensity of peak C, which is this one here, the 12 outside of this summation here, divided by that of the intensity of peak A, we find that is equal to 20 because we are using the information from the intensities now. Okay, so this expression here for peak C, the intensity was measured to be 1, and the intensity of peak A was much smaller, remember, and it's 0.05. That's how we get the 20 there. Okay. So what you can do is then, has anybody got the time? Is that right? Because my time's sort of died here.
Yeah.
What time is it? 10 to? Thanks. Good. Okay. So, so from our data, you see we had the intensity of C to intensity of A is that 12 BPR plus 2 B of O, all squared, over 8 BR, which is the scattering strength of the praseodymium atom, equal to 20. And, okay, so you know, you can basically solve this. You'll end up with some quadratic minus 148 VPR squared plus 48 VPRBO plus 48 VPO squared equals to 0. And, you know, you can solve that using, you know, your usual, if you remember, b squared minus 4ac for quadratic 10. Then we can find, you do it, you will basically find that the scattering strength of a praseodymium atom is equal to 0.162 that of the oxygen atom minus or plus 0.59 B0. So you get a choice basically of it being equal to 0.75 that of the oxygen atom, or an unphysical value of minus 0.428 B of 0. Since we don't have negative intensities, yeah, this is the result that we've been able to obtain from that scattering information. So in this case, you know, for neutrons, even though you might think the praseodymium atom is much heavier, it's much bigger, we can actually see that its scattering strength is 3/4 that of the oxygen atom. So from that experiment, we've been able to obtain some interesting information. First of all, the lattice constant of the material and its structure, and then some information about the scattering strength of the atoms of that material. So I'm just going to leave it with a little overview of some interesting in practice. Okay, so people study really complicated crystal structures like, you know, some proteins and things. And nowadays there's lots of, you know, computer programs that will really assist you in analyzing your spectrum really pretty quickly. As I said, you can really study complicated materials now. For example, you will somehow crystallize a protein on a specimen and then put it into the either X-ray scattering facility or probably not neutron scattering, but possibly neutron scattering. And, you know, around the world there's lots of, you know, very, very good facilities. The Spring 8 in Japan for X-rays, the Australian synchrotron. You know, you might go down there if you continue in physics and do experimental physics. You might do some work down there. That's nice apparatus. Or, as I said before, at ANSTO, they've got lots of neutron scattering experiments. You can see here, there's many. That just gives you an overview of the experimental hall. They've got many different kinds of experiments. All of these labels are different kinds of experiments that you could do. And they are all labelled after Australian animals. It's interesting. And of course, here is a very famous one, the Diamond Synchrotron light source in Oxfordshire, and the spallation source right next door to it. And yeah, there's one neutron source being built in Sweden for a large amount of money, but not comparable to the you know, the Large Hadron Collider or so. Let me see here. As I mentioned before, you know, reflection, high energy electron diffraction, that's another diffraction technique that you can use. Because the surfaces are so important of materials, as they're getting smaller and smaller, we need to know also about what the atoms are doing on the surface. And to do that, you would use this kind of reflection, high energy electron diffraction, where the incident light just comes at a grazing angle, so it's really surface sensitive. The the radiation doesn't penetrate deep into the crystal. It just within the first few layers, and this is the kind of results that you get. And basically, you monitor this as perhaps you are growing a film of atoms on the surface. You might start off growing it, and you can see it's only half complete. And at that point, when it's half complete, it's schematically shown here, the intensity of your peak might be low. When you get a complete layer, for instance, you'll see a maximum in your intensity as you're growing it. So this is often used in situ while you are growing your material. This is another really nice one that is surface sensitive. For example, this shows a 7x7 reconstruction on the silicon 111 surface. Under here you can see just the ideal silicon 111 surface. But this material, because of the surface, the atoms no longer experience the same environment as they're in the bulk. So they reconstruct just spontaneously. And there was quite some, I guess many years now, trying to figure out what this structure was. And so you could solve it using low-energy electron diffraction. That's the kind of spots you get. In this case, notice the energies are much smaller, 20 to 200 eV. You shoot in at your crystal, and rather than going through, like in X-rays, these beams are collected, they reflect back off, and you collect here. So this is what you are seeing bounced back at you. And low-energy electron diffraction is much more complicated to analyze than X-rays because you have multiple scattering events. The electrons can bounce off an atom and then scatter multiple times. Okay? But there's codes available, like everything nowadays, that can allow you to really simulate very accurately what you measure experimentally. See here, this is normal incidence, which means it's coming straight perpendicular to the sample. And because it's a surface, we don't have 3 milliindices. You only have 2. For example, the -1 and 0, -2 and 0, so on. So this is the intensity here for a particular spot as you scan the energy. You can see you get quite complicated curves. But as I said, with the codes nowadays, it's been a lot of development. If you get the right structure, what you do is you guess a structure in your code, right? You put the atoms where you want, you run the code, and you can simulate these curves. And then what you do is you align them with the experimental ones, and when you have the right structure, you will get very close agreement, which is the case here. It's pretty good. And the agreement is quantified by, some kind of error analysis. It's called an R factor, where it just measures the deviation with the experiment. So, yeah, if you get the structure wrong, if your guess is wrong, there's no way you can, get any kind of good agreement. So, it's probably the most accurate way of getting surface structures, the atomic position of atoms around. I mean, you can use scanning tunneling electron microscopy, STM, where you get these pretty pictures. But what you're seeing is not necessarily the positions of the atoms, you're seeing the position of the electron densities. But, we'll get to that a bit later on. I better leave it here, and we'll carry on tomorrow. I can't take questions, I've just got to run to a tutorial.